Hi, everyone. So for this unit, we're talking about two major topics that are very similar in terminology, but are kind of opposite in concept, but they do connect together. The first thing that we're going to talk about is referred to as kinetics, but what it's really referring to is something called a reaction rate, or how quickly or how slowly a reaction proceeds over time. So, in general, when we talk about anything referring to a rate, we're measuring the amount of any change that occurs within an interval of time. So, the most common rate example is speed in your car. You drive a certain number of miles over a certain amount of time, and there was a certain rate or speed that allowed that to happen. The rate of a reaction is actually entirely dependent on the energy diagram for the reaction. So this is something that we've seen before, but I just wanted to take a quick second to recap some of the more basic principles of this thing. So remember that the y-axis is always referring to the amount of energy, and we said that the x-axis was something called the reaction coordinate, but I always refer to that as time. So at the beginning of a reaction at time 0, we're starting as reactants, we're ending as products, and then that hill to go from the reactants to meet this necessary energy, which we refer to as our activated complex, there was a required amount of energy that had to occur, and that's the key part here. Is what we refer to as that activation energy. Okay, so reactions that have a small activation energy can occur quickly because they don't need a large amount of energy to be applied. And the reactions that might have a much larger activation energy will occur slower because they need a larger dose of energy for that reaction to occur. Right? So from the video and the lab that we did at the start of this unit, we talked about some major things that can cause a reaction to speed up, things that affect the rate. And so we always have to think in terms of that it can either increase or decrease the rate of the reaction, make it go faster or slower. So when we say temperature, in terms of increasing the rate, raising the temperature of a system will cause the rate to increase. Okay, and remember the opposite holds true. Cooling the temperature down will slow the reaction rate down. Okay. Concentration, again, is referring to molarity. So how densely concentrated or how many moles of solute can we pack into a particular beaker or solution. So increasing the concentration will increase the rate of the reaction. Putting more material into the system will cause it to collide more and cause the reaction to speed up. And then particle size is what we refer to as surface area. Okay, so increasing the surface area speeds up a reaction. And the image off to the right is a really good one that shows how this takes place. So the red particles here are acid particles. The blue particles here are water molecules that the acid's dissolved into. And then these black particles down here represent magnesium. And so this is actually similar to the lab that we did yesterday, but instead of actually breaking up the magnesium, we just kept it as one whole piece. But if we look at this as like a rectangle, these atoms here in that middle row aren't going to come in contact or collide with these acid particles because there's a layer of magnesium atoms around the perimeter. By breaking up the reactant into a bunch of smaller pieces, there's no center atom, so everything is exposed on the outside, so it increases the likelihood that these acid particles can collide with a magnesium particle. Okay. And the last thing we talked about speeding up a reaction is something called a catalyst. So adding a catalyst to a solution which increases the rates. Okay. So the one thing that we have to remember here with a catalyst is that it's something alternative to the reaction. So it's not a necessary reactant in the system. So the most common example that we use every year as a catalyst is an enzyme. Do you remember from biology? Enzymes are part of a necessary biological pathway that helps a particular biological reaction to occur. And then another common example that I like to use in terms of a catalyst is in the muffler of your car or a car, right? A long time ago, they didn't have a particular modification on all mufflers of a car that just allowed all these like harmful gases that an engine will produce to just go out into the atmosphere. And then they realized that by adding platinum or palladium as a catalyst, a lot of those gases will react inside the muffler and turn into less harmful gases. So a catalyst is just something that the reaction can occur on or allows the reaction to occur really quickly, but it doesn't actually chemically get consumed or contribute any like matter or any atoms to the chemical reaction. Right? So all of these things that affect reaction rate summed together are what we refer to as the collision theory. All right, so the collision theory focuses on two major things: orientation and energy. Right? Not all particle to particle collisions result in a reaction. So just because two particles bump into each other doesn't mean they're going to chemically react. All right, every time you high five to somebody, your hands would chemically react with the other person's hand if there wasn't an activation energy that was required. So if particles are moving faster, they're not only more likely to collide just from them moving around at a faster speed, but they're more likely to collide and react. So particles that are moving faster have more kinetic energy, which is the energy of motion. Right? The other thing that I want to talk about is orientation. There's a certain arrangement that these particles have to hit in order for the reaction to actually occur. So like in this example, these center particles of the magnesium atoms won't necessarily collide with the acid particles, so if they hit, they won't necessarily react. There has to be a particular orientation or alignment for the reaction, kind of like the enzyme example, and there has to be enough energy for the reaction to occur. Okay? So the next part that we're going to talk about has to do with reactions occurring in what we call both directions or reversible. Okay, so this is referring to how we take any reaction and speed it up or slow it down. And in this unit, we want to introduce the concept of something called an equilibrium. And an equilibrium only occurs when there's something called a reversible reaction. And that's a reaction that occurs simultaneously in both directions. So this reaction here, we've got 2SO2 plus O2 comes together, synthesizes to form 2SO3. Well, if these are all gases and they're happening inside a closed container, isn't it possible that this particular molecule could decompose and reform the things that it made? Right? And it actually is connecting back to this idea of an energy diagram. The reactants have a smaller energy requirement to turn into products, but the products still have some pathway to reverse back to these reactants. It's a larger energy requirement, and it's not going to happen as likely, but it's still entirely possible that the products could get that necessary amount of energy to turn back into reactants. So the symbol that we're going to use is a pretty simple one. Anytime we see one arrow, that's indicating that the reaction is happening in one direction. But if we have both reactions occurring, where this is basically making these reactants again, we use what's called an equilibrium arrow. So this is indicating that these reactants are going to combine together and make those products, but this product can also decompose and go back to make those reactants. Okay? So in terms of the rates, a chemical equilibrium is reached when the rate of what we call the forward reaction is the same as the reverse reaction. So every time these three molecules collide together to make those two products, somewhere else inside the container, those products are breaking down and making the same amount of those reactants, essentially keeping the amount of everything constant. Okay? And so this is our first time looking at something this particularly new. So at first glance, this seems kind of like, what are you talking about? So hold on, we'll get there, all right? But I just want you to keep in mind that one, a reversible reaction is possible, and two, when we talk about equilibrium, we're talking about how quickly these reactions are going to occur, and then when their reaction rates are the same, that's when an equilibrium has been achieved. Okay? So I want to talk a little bit more about some of the terminology that we're going to see in terms of an equilibrium. And then in the next video, we'll be able to get a better visual of what it actually means to have achieved an equilibrium. Okay? So again, for these types of reactions, we're going to use something called an equilibrium expression. And that's an equation used to express the relationship between the concentrations of products and reactants in a reversible reaction. Okay? So each of these reactions should actually be reversible reactions. Okay, so we're going to talk about these happening in both directions. The symbol for what we're calling the expression is a K value, right? And then the units are actually that there aren't any units. We're evaluating the concentration of the reactants compared to the products as both reactions are occurring at the same time. Okay? Now, when we talk about ways that we can cause a forward reaction and a reverse reaction to speed up, we said that temperature, catalyst, and changing the concentration and particle size are the four ways to make that reaction speed up or slow down. For this reaction, where we've got these reactants and these products dissolved into water, the only way that we can really adjust the equilibrium is by changing the concentration. So we're looking at these coefficients as a ratio of your reactants and how many you need compared to your products, right? So as two A's combine together to make one B, we're going to form 3C and 1D. So this K value is always going to be written as an expression of how much product is made compared to then how much reactant is made for the reverse reaction. So in general, K is always products over reactants. And because we need twice as many A and 3 times as many C, the amount that is required for each reaction has a particular impact on this equilibrium expression. Okay, so for K, we're going to start by writing out the concentration of our two products, and we're going to multiply those together. But because we need 3 times as much C, this concentration of C is going to be a cubed value because it's 3 C's. So C times C times C. So we say C cubed. And then on the reactants in the denominator, we're going to do the concentration of our A reactant times the concentration of our B reactant. But because we need twice as many A, it's A times A, or we'll say A squared. Right? Now, all of these things occur either in water or as a gas in a liquid or a solid inside a container. And so the one thing that we'll talk about next are ways that these equilibriums can be achieved and disturbed. And so there's certain things that are excluded in an equilibrium expression because we can't adjust them based on their concentration. And so the two common exclusions are solids and liquids. So when we write our K expression, anything that is a gas or gets this AQ designation, which means it's dissolved in water or is aqueous as a soluble solution, we're going to include that into our expression. Here, for this equilibrium reaction, we've got a gas, a liquid, and 2 gases. Now, the thing with water as a liquid is we can't concentrate water. You can't make 2 molar water because it's water dissolved in water. So you can't dilute water, you can't concentrate water. So since you can't adjust its concentration, there is no concentration value for any liquid. So that's why liquids are excluded, and it's the same reason why solids are excluded. So when we're determining the K expression for this reaction, again, we're going to focus on the concentration of our products multiplied together, and since these are each 1 and 1, they're both to the first power, and this is all over how many carbon monoxide molecules are going to form at equilibrium. So we just completely exclude the H2O because it's a liquid. Right? So this K value is just saying how much product and how much reactant is present once equilibrium has been achieved. And the K value itself will actually have a number value that is related to. Okay, so again, K is always products over reactants. So if K is greater than 1, then that means that the numerator of your K value is larger and the denominator of your K value is smaller. So that means that there has to be more products than reactants at equilibrium. And then oppositely, if K is less than 1, meaning it's a decimal, then you have to have a large denominator and a small numerator in order for that fraction to equal any decimal value. So a large denominator means that there are more reactants at equilibrium than products. And if for some reason K is perfectly equal to 1, then that means your numerator and your denominator are the same value, and that means the concentrations of your reactants and products have to be the same. So what does all this mean? Right? If we have this equilibrium reaction, A forms B, and at the same time, simultaneously, B goes back to form A, and we're told that our K value is equal to 0.25. Okay? Well, the equilibrium expression as products over reactants is the concentration of B over the concentration of A. So once equilibrium is maintained, whatever my number of B's are and my number of A's are, regardless of how many I have in the system, always has to be at a ratio of 0.25. Okay, so if K is less than 1, that means A has to be a really large value and B has to be a really small value. So at equilibrium, the container is predominantly A's or reactants. Okay? So if this is like my initial conditions, and this is my equilibrium conditions, okay? We get 1A to chemically react and turn into a B, right? And then we've got 1, 2, 3, 4 A's left over. So technically we've reached equilibrium because now I've got 1, 2, 3, 4 A's and only 1 B, and that's equal to 0.25, which is the K value that's determining how many A's become B's and how many B's become A's. Right? Now, what's actually happening is this is constantly changing about because the system is constantly in equilibrium. So every time one of these A's chemically becomes a B, that B is now going to reverse back and form an A, constantly keeping 4 A's in the system and 1 B in the system. And so this is obviously just like a simplified analogy, and it could completely change based on how that K value changes. But this is, again, still very much at the beginning of this idea, but a good example of what it means for a system to be at equilibrium.